Okay, folks, we're going to start chapter 10. Usually, probably the last 3 or 4 years, I've included chapter 9 and chapter 10 into one test. We'll see. I think going through chapter 10 right now would be a good thing per our situation. By the time we get far enough in chapter 10, I think we'll have a little bit more information from the governor on whether we're coming back to school, when we're coming back to school, or what. And that'll allow us to maybe better decide on how I'm going to operate with tests in this online format. But chapter 10 is all about area. Okay, so we're going to run through a bunch of area formulas here. One thing to note before we get into any of this, a lot of our properties from chapter 6 are going to pop up, okay, and be necessary. So that was, if you remember, chapter 6 was about polygons, quadrilaterals, rhombuses, squares, rectangles, that type of stuff. So the features that existed there are going to be used here. And area is going to segue into surface area in the next couple chapters, okay? One thing I want you to know is, well, before I say that, it's not only going to segue into surface areas, but then area is the basis or the foundation for volumes. So chapter 10, if we learn chapter 10 real well, it's going to make 11, 12 so much easier. If we don't pick up on these area formulas and we don't learn them to the best of our abilities, surface area and volume are going to be things that cause a big issue for you. For the most part, some of these formulas you already know. We're going to maybe look at them in a different perspective. And a lot of the things that we do in this chapter, because it is, a 9th grade, 10th grade course now instead of 7th and 8th grade or 6th grade. I'm not just going to say, here's a formula. Here are the values to put in for the formula. You go ahead, substitute, and evaluate. There's going to be a little bit more critical thought involved than just taking a formula and filling in the components, okay? First thing we'll start off with, we've got a postulate, and essentially a postulate is defining what area is for us, okay? So the area of a square is a square of the length of a side, okay? Basically saying you take the side and you square its amount, and that's going to give you the area, okay? Area is the square units, the two-dimensional surface that an object encompasses, okay? I don't know if I've got a defined definition from your textbook here for area. I do not. That's kind of maybe the best way of thinking of it. So essentially, if I have any shape, how many unit by unit blocks can I fit inside that shape? It's how much two-dimensional space a object contains. Something to think about when we talk about two figures that are congruent, then they're going to have congruent areas. They have congruent distances. Therefore, when those distances are transferred into the formulas, the products and sums and differences that are used inside the formulas are going to generate the same results over and over again. Okay. In all of our problems, there's usually an altitude, or all of our formulas are usually an altitude. Okay. And we're usually going to label it with an H, which again, we've talked about can be problematic because we think sometimes that H has to be vertical because we think it's a height. What I want you to remember is an altitude, like we talked about in triangles, is in a triangle, it starts at a vertex and goes perpendicular to the opposite side. But in all figures in general, essentially it is a segment that connects opposite sides in a perpendicular fashion. Okay, so it says to a base, an altitude is any segment perpendicular to the line containing the base from any point on the opposite side. So if I want to start here, if I go perpendicular to the opposite side, there's an altitude. If I want to start there, perpendicular to the line containing the opposite side, there's an altitude. Okay, if you think about this blue dotted line down here kind of being your desk, and this being, if you guys remember back to like 7th and 6th grade, maybe 5th grade, you had tanagrams, and you would put them, they're blue, yellow, red, orange, and you put them together. If you took one of those tanagrams and set it up on your desk and measured from that corner straight down, that would be essentially the height or the altitude of that tanagram. So your altitudes can be outside your shape. Now, what kind of tends to be an issue for some people, and this especially happens with this parallelogram, is that if I can start right here, so I'm on this side here, okay, and I'll go perpendicular to the opposite side. That could be an altitude as well. Okay, now if that's the altitude, then this would be the base that I chose. Okay, we'll get into some pictures here in a moment that investigate that, but that can be a little bit tricky for some people. Over here we got trapezoid. Okay, in this case, these altitudes that are drawn are my only options, and for some of the things that we've done in the past, that altitude and that altitude make the most sense to draw. This one is equivalent, but it doesn't make as much sense as the other two because the other two create these triangles, and that's going to be useful to us. Let's keep going on. All right, so the area of a rectangle equals the product of the base and height. Okay, so if I go from there perpendicular to the opposite side, there's our h, there's our altitude. And remember, by definition, altitude connects two bases, so this must be my base. So we call it b. If I multiply h and b together, it gives us the area formula for a rectangle, which is basically going to tell me how many of these kind of 1-by-1 blocks or unit-by-unit blocks can fit in there. And it's simply multiplication. If you think about, like, if I had a ceiling of tiles or a floor of tiles, and I wanted to know how many of those tiles fit in this ceiling or floor, I could count them all individually, or I can go 1, 2, 3, 4. Got 4 there. 1, 2, 3, 4, 5, 6. I got 6 there, and that multiplication gives me 24. So 24 of these individual blocks will fill that thing in, and that's essentially area. Okay. So that's our rectangle formula. You guys should be familiar with that. Sometimes you call it length and width. That's fine. Our textbook is going to use base and height. All right, so here's a parallelogram. And ultimately what I want you guys to recognize here is this is the same formula as a rectangle. Okay, think about a rectangle. A rectangle is a parallelogram. It's a special kind, but this is still going to have the same formula. Okay, so here is my altitude. And remember, in a parallelogram, when we have that altitude perpendicular to these two sides, then those two sides are bases. So there's my B. I'm going to multiply those together. I get 60 square units. So I'll just use U for units. Now, what I want to talk about here briefly is why is this a same formula as a rectangle? If we were to do that, we got that right angle, come over here, got a right angle there. This would still be 5. Okay, got a right angle. By definition, or not, I guess not definition, but one of our properties of parallelograms is that opposite sides are congruent. So right now, we have And we also know opposite angles are congruent to parallelograms. We have that information. We have quite a bit of information going on here. And if I think about it, I've got either think about this triangle here being congruent to that one by hypotenuse leg, or congruent to that one by angle side. Okay. So let's kind of do something here. If I call this, we know that this distance here is 12. This whole thing here is 12. I don't know what that is, so I'm just gonna call it X. Okay. So this here would be 12 minus X. Okay. Now this triangle here, it's the same as this one. What I'm going to do, so this would be X here as well. Okay. What I'm going to do is I'm going to take this triangle here. I'm going to cut and paste it. I'm going to move it right there. Okay. So what I do, so this is going to be X now. Okay. And I'm going to kind of clean this up a little bit. Let's just erase. Erase this here. So I've cut and pasted that triangle away. And now all I'd be left with is this distance. Well, that distance by the segment addition postulate is that X plus this 12 minus X. Well, what's X plus 12 minus X? It's still 12. And this distance here is still that distance there, so it's still 5. So as I cut that little triangle off and replace it over here, I just reorganize the area, okay? And the shape that I create now is that rectangle. And what's the area for that rectangle? It's base times height. So what would be the area of that shape when I reposition it back like this? It's still base times height. So that's kind of the logic on why those two formulas are identical. One thing to think about with a parallelogram is that you have two sets of bases. Bases in a parallelogram are just your parallel sides. So you have altitudes that could come from different positions. Here, I think this picture here is the one that most people are comfortable with and are thinking about when they talk about a base of an altitude of a parallelogram, okay? But over here, this could be an altitude as well, because by definition, it starts on one base and goes perpendicular to the line that contains the other, okay? So this would be also an altitude. The one thing to think about is that altitude there, though, is not going to be necessarily the same as that altitude in terms of its size. Likewise, this red base here is not going to be the same as that red base in size. Okay, so those are things to think about when we're working with parallelograms. All right, so this rendering here just kind of demonstrates the idea of our different altitudes for a parallelogram and how we can kind of discuss those. The first thing I want to talk about here is that number right there, I believe, is the area of this thing. Click on that. Yep. Okay, so that's the area of my quadrilateral, 38. So I'm going to use that here in a little bit to kind of justify some ideas or concepts here. If I'm talking about this parallelogram, I think most people, I'm going to let this black line here be my desk. Okay. If I put my black line right there and I ask you to find the altitude of this, I think most people are going to say, well, that's going to be the line that is maybe right. Let's go. There we go. Maybe that line right there. So let me get another intersection point here. So that intersect with that. Okay, so we're looking at then this segment J to K. And I'll get rid of that line. So that segment J to K, or they're calling that L, so I'm just going to make it red. Okay, so that segment right there is my altitude. Okay, and I can move that around. Most people are probably going to come up with the altitude right there, or they might, and that's what I was afraid of. Let's do this. Let's remove K. Okay, so I fixed this. So now most people, like I said, are going to think about that red distance there, or they come over here and put it there and think about that red distance as being your altitude. Well, if that's the case, and looking back at this one, if that's the case there, if that's my altitude, then D to F would be my base. Okay, so what I'm going to do here is I'm going to say my altitude, which they're saying was, I'm not sure what letter this is, I to L. So we'll take I to L. That's my altitude. That's H. And I'll multiply it by my base, which my base is D to F. And if that is done correctly, those distances, when I'm multiplying them together, should give me 38, which we see as, where'd the number go? There we see the number 38. Okay, you see it's IL times DF there in yellow. Okay, so that's great. That's awesome. But if I look at that distance, IL's distance right now, let's just see if I can get this thing to show that distance of IL. 2.96, and if I look at the distance D to F, F to D, there you go, 12.85. So if I take those two numbers, multiply them together, I get 38. Okay. Now, something that you have the ability to do, and not many people do this, but is the potential to actually take this shape, and instead of laying this base on your desk, you could lay, let's say, so I'm going to take this quadrilateral, and this might be a little messy here in a moment, but I want to take and rotate this quadrilateral around that point. Let's say we're going to go by, I don't know if C is an option. It is, okay. All right, so now I'm going to go. Okay, so some people may rotate and set, or not rotate, but kind of move their rhombus so that it looks like this, and their desk then, I'll move this number to 10. And now this is their desk. Okay. Well, if they do that, okay, this red segment is no longer the altitude that they'd be using. They'd probably be more thinking about that altitude right there. Okay. So let me take a moment and I'll figure out I'll get this thing to show that altitude. So we'd be looking at this distance here as being our altitude. Okay. Now that could also, and I don't have it set up this way, but I could take that segment and slide it so that it was like right here or maybe right there. But there's no way that I can draw this blue segment so that it intersects that little segment there. That's why we have to have the definition that an altitude is perpendicular to the line containing the opposite side, because sometimes you might not be able to actually touch the opposite side. There's no way I can go from D here, or D prime, perpendicular to any point between F prime and G prime. But this is the same figure as down here, but now this would be my altitude. So let me show that distance. So that distance would be that number there, so 7. And then D prime to E prime would be my base, or F prime to G prime would be my base. They're the same. So let's put that as 5.43. Now, what I want you guys to understand is that neither of those numbers are the numbers that were down here. The bases and altitude down here where 12.85 was the base, the altitude is 2.96. The shape rotated. Now I've got this altitude of 7 and this base of 5.43. But what I want you to understand is this was a rigid motion that I did. It was a rotation. So I didn't change anything. I didn't make this thing grow or shrink. So the area that this quadrilateral down here encompasses better be the same as the area that this one encompasses. So if I take the base and height here, so d prime times e prime, and multiply that by d prime times n, okay, when I do that, I should still get the same exact 38 that I got down here when I took 2.96 times 12.85. So I want you guys to understand that when we work with the parallelogram, the base times height formula is true, but you might use a base and a height that is different than what I use or what your neighbor uses, but you both still get to the same total area. So that's just something to think about. And that's really what this slide here was getting at. Okay, so here's some examples. Finding the area. Okay, I'm not going to do the multiplication here, but the area is b times h. So this is your altitude, so 4. And this is your base, because that's what the altitude is drawn to, so that's 5. So again, that's 20. Now it's inches times inches, so it becomes inches squared. Okay, that number there to confuse you. Okay, same thing over here. Okay, now this is a situation where the only perpendicular distance that we see over here is this 3.5. So that 3.5 must be my h. And then which of these two numbers do I use for my base? Well, it's the number or the distance that the altitude is drawn to. So the altitude is drawn to that side. So our area, base times h. And then, so base was 2, h was 3.5. So that's 7 centimeter times centimeters. So that's centimeters squared. I know I said I wasn't going to do the math, but it didn't turn out to be that difficult. So those are two examples of finding the area of a parallelogram. Okay. Now this is where it's no longer like 6th, 7th grade math. Okay. They give me this information and they ask me to find the area. Well, here's my altitude. Okay. We know base times height. So we know the base is going to be 31 because that's what the altitude is drawn to. Now I got to find this h. And how do we do that? Remember, this is a 45, 45, 90 triangle. So in 45, 45, 90, this is n radical 2, this is n, that's n. So right now, that and that are equal. Okay? So then n radical 2 is equal to 12. I'll divide by radical 2. I can rationalize that. And I get 6 radical 2. And that then becomes this n right there, which if we lay this triangle on top of this one, it's the same as that. So my h is 6 root 2. And now when I multiply base times height, okay, you have 31 of these things. Okay, so 31 times 6 is 186. And then radical 2. And there's my area. And again, it would be units squared, whatever, inches, centimeters, meters, miles, kilometers, whatever. The area of a triangle, okay, so you guys are familiar with the area of a triangle, 1/2 b times h. Kind of talk about that real quick. Any triangle you ever draw, if this is b and that's h, or go this way, this is h, this is b. When I do that, I now have a triangle, 2 triangles. And these triangles are congruent, okay, because so let's do it this way. So we have those congruencies because it's a rectangle. This segment's congruent to itself, so the triangle 1 here and triangle 2 are congruent. So if their total area is BH, total area is BH for the rectangle, then each individual triangle would be half that. You can see that it works with a triangle like this as well, because if I were to do this, these two triangles are the same. These two triangles are the same. Okay, so the white area there, the white area of this rectangle would be equivalent in size to the yellow angle in that rectangle, or yellow area in that rectangle. So then the rectangle's area formula is BH, so the triangle is 1/2 BH. One thing we got to pay attention to here, and this is what you're kind of trained to do in 6th grade, 7th grade, 8th grade, is that you worked so much with right triangles. And with a right triangle, okay, it doesn't matter. This is B and that's H, or this is H and that's B. It doesn't matter because they're both altitudes. Both segments here, both sides are altitudes in a right triangle. So a lot of times you just took the two sides and multiplied them together and multiplied by 1/2. You don't always do that. So I just want to make sure that we don't end up doing that in a lot of the situations that we come across. I'm going to skip that problem here. Skip that one as well. This is kind of what I was talking about, is if I want to find the area of this triangle, actually, not even this one. Let's kind of come over here to maybe a triangle like this, where I've got, I don't know, let's say 6 and let's put 20 here. And I'll put 30 there, 30 degrees. What I see in the past is somebody trying to find the area of this. There's a lot of times they'll go 1/2. Okay, the two sides they gave me are 6 and 20. I'm multiply those together. That is wrong. Okay, because neither of the 6 nor the 20 is an H. Okay, an H, remember, is an altitude, so it goes from a vertex perpendicular to the opposite side. That distance there is going to be shorter than that 6, and it's going to be less than that 20. Okay, so that's my H. And if you remember anything about special right triangles, which we should because we're going to use it a lot, that H ends up being 3 in this case. So the area of this triangle would actually be 1/2 your base of 20. 20 because that's the side that the altitude is drawn to, and then the H, which is 3. So it's going to be 30. Up here you would have gotten 60. That's obviously wrong. So that's what I want to make sure we understand, is that when we're working with the area of triangle, it's just not just any two sides that are B and H. They're specific. You got to know what the definition of H is, what altitude is. This triangle here, I'm going to find the area of that. So this shape in general is called a composite shape. Okay, composite is a word for when things are merged together. Okay, when you compose a paper, you merge together ideas and structures like introductions, thesis statements, a body, conclusion, and then obviously all the ideas that are written inside those things, and you compose something. Okay, if I'm composing a musical composition, I'm taking a bunch of notes and harmonies and choruses and those types of things, merge them together in one piece, and I compose a piece. So a composite image is multiple shapes being merged together. And we'll see a lot of that throughout the next couple chapters. So if I want to find the area of this thing, we got to break it down to kind of common shapes. Right here, we're seeing that this is a square. Per the information, 4 congruent sides, 2 right angles. We know it's a square, it's 6 by 6. So that's going to be 36 square inches. Remember, the area formula for a square is S squared. So we get 6 squared, which is 36. Now the triangle is 1/2 B times H. The nice thing here is that that distance there is perpendicular, starts at a vertex, goes perpendicular to the opposite side. So that distance is h. So h is 8. Now the opposite side, that side there, is my base thing, is what the altitude is drawn to. What is that distance? It's the same as that distance, so it's 6. So we get 1/2 times 6 is 3, times 8 is 24. So now what do I need to do to get the total area here of these two things? I add them together. My total area is 60 square inches. Down here, so it's a trapezoid. Same idea. Now, just thoughtfully, you have to understand that this may or may not be a rectangle. Maybe a square. Don't know. Okay. Looking at this triangle here is a right triangle, and you don't know. This is a hypotenuse. Your hypotenuse is not a base. Okay. In most situations, it could be if that were the altitude that I drew to it, but usually we don't like doing that one. What I'm going to do here, I'm going to work around and I'm going to try to figure out what this dotted distance is. Okay, so this is a right triangle. So the Pythagorean theorem should work. So if I call that A, I should be able to say A squared plus 7 squared should equal 25 squared. Okay, so then A squared is going to equal, so 625 minus 50 would be 575. So this is 576. We want to subtract 49. Square root of 576 is 24. Okay. So we get 24 there for A. Let me just double check that. I don't want to make an error there. Okay, I recognize that as I was making this video, I paused it at some point and I forgot to unpause it when I finished things. So let's come back up here real quick. And I may have done this. I think I paused it when I was verifying this 24. So let me just kind of delete this out here and we'll start over. I apologize for any repetition that might happen here. But when I want to find the area of this triangle here, area is 1/2 BH. So it's 1/2 the base. Now either one of these, the 24 or the 7, could be the base because they're the sides of a right triangle. So I'll just say 24 and then 7 as my H. So those are going to make 12. So 12 times 7 then gives me 84. Okay, so 84 is the area of that triangle. Finding the area of the rectangle then is going to be base times height, which is now the base is maybe 21 and the height is 24. It doesn't really matter. 21 times 24 is 604. So now to find the area of the trapezoid, I'm going to take that and that, add them together, and we get 688 and be feet squared. Going on to the next one, we have a kite here. Let me erase this stuff. Okay, the only thing with a kite that we have to know to do this is that the diagonals are perpendicular. So you got a bunch of right angles here, so right triangles. We talked about that triangle and that triangle are the same. This triangle here and that triangle there are the same. So I'm going to find just the area of triangle 1 and 3, add those together and double, and it'll give me the area of the entire kite. So the area of this triangle here, 1/2 BH. B, I'm going to let be this 5. And H is going to be that 4. So it gives me 1/2 times 20, so 10. So that triangle is 10 square units right there. And so is that one then. Okay. The area of the triangles on the left is 1/2. They're saying that distance there is 2. And then remember that distance there was 4. So I multiply that, gives me 8. So both these two triangles on the left are both 8. So if I double that, so this is going to be 20. This is going to be 16. Add those together. Oh, sorry. This isn't 8, that's 4. 2 times 4 is 8, times a half is 4. So it gives me this to be 8. So 20 plus 8 then gives me 28 square meters. And then finally, I think the one that's the most difficult on this is this question here. Again, let me clean it up. All right, so that's a trapezoid. We got a triangle and a rectangle. So I want to find the area of the triangle and then the area of the rectangle. Okay, both of them need that distance there. If you remember a 30, 60, 90 triangle, and this is where, at the beginning I told you it's not going to be like, 5th, 6th, 7th, 8th grade math where everything is explicitly given to you. You're going to have to do a little bit of work. If you remember a 30, 60, 90, so this is the hypotenuse is 2n, cross from 30 is n, and this distance here is n radical 3. So in this case, 2n is the same as 4. So it gives us our little equation, 2n equals 4. So n is 2. N is that side there, which is right there. And then this distance here ends up being the 2 radical 3. Now the nice thing is that gives me the area of a triangle is 1/2 BH. So we have to figure out what is our base, what is our height. Well, it's a right triangle, so it really doesn't matter, but I'm going to let that one be my height. So 2 is my height. And this one here, then, the 2 radical 3 would be the base. Or when I multiply the 1/2 and the 2, they cancel out. I'm left with just 2 radical 3. The rectangle, then, is base times height, which is 2 times 8, which is 16. So now, the area of a trapezoid, right now, is the area of that triangle, plus the area of the rectangle. The area of the triangle is 2 radical 3. Area of the rectangle is 16. These are unlike terms. Okay, remember radical 3 is an unknown value. It's a 1.7. We know it's a symbol though for something that another number. So it's just some symbol. Okay, so let's say it was x. If it was x, would you add 2x and 16? Would you make that 18 x's? No, you can't do that. They're not like terms. So for the same reason, 2 radical 3 and 16 are not like terms. This is an irrational number, and this is a rational number, and they are not from the same group of numbers, so we don't merge them to make another number. We just leave it as 2 radical 3 plus 16, and then we tag on our units, so feet squared. There's going to be a Math Excel assignment that is attached to this, 10.1. Plug away at that. Shouldn't be entirely difficult. We will progress the difficulty eventually with these formulas and the problems that you see with them, but I'll do that through the use of some worksheets. So those will be on their way to you soon. But right now, for this session, all that is due will be your Math Excel assignment 10.1.